Hey people, we are back for some more chemistry fun. If you take a look at your content objective for today, we are going to be able to evaluate an overall reaction as expressed by reaction mechanisms to determine which step of the mechanism is consistent with data regarding the overall rate of a reaction and identify the presence of what's called a reaction intermediate. So I know the College Boards throw some things at us to understand that can be a little tricky to decipher. So again, let's break it down a little bit. There's a lot of new vocabulary we're going to be talking about here, but we're going to look at how we can define what's called a reaction mechanism, which is essentially a step-by-step process. Ooh, baby. Step by step. Oh, baby. Oh, man, it was such a great time. Anyway, it's a step-by-step process that adds up to the overall reaction. Two, we're going to identify what's called the rate determining step in that reaction mechanism and explain how the rate of the overall reaction is determined by that step. And then lastly, we're going to define what's called a reaction intermediate and explain its role in that reaction mechanism. So you probably are no more clear on what it is that we're going to be doing based off of that breakdown, but stick with the notes here. And when you come into class, we'll do a couple of demonstrations that I think will really clear up what a reaction mechanism is, what the intermediate is, and how to work through these types of problems. Okay, so in general, we typically describe a chemical reaction with an equation that lists all the reactant molecules and all of the product molecules. However, what you may not recognize is that most reactions actually occur in a series of much smaller steps that involve, again, probably 1, 2, or at most 3 molecules. And again, it goes back to the idea that we discussed in collision theory that, it's going to be really rare that you can have 3 or more molecules that are going to come together with the exact right orientation and the exact amount of activation energy that is needed for the reaction to occur. And so even though we typically see all these brilliant, really long equations with lots of reactants and lots of products, there's generally a lot of smaller steps that occur in order to make that reaction happen. So when we describe the series of reactions that occur to produce the overall reaction, the observed reaction, we call that a reaction mechanism. So as you take a look at the example that's in your notes, here's your overall reaction that we typically are used to seeing, expressing, and then here's your reaction mechanism that's broken down into 2 elementary steps. Now, the reaction mechanism, again, is just sort of the sequence of the bond breaking and bond making steps that led to the overall chemical reaction. Again, each individual step is called an elementary step. Again, if one reactant is involved in an elementary step, we call that a unimolecular elementary step. If we have 2 reactants that are involved in the elementary step, it's called bimolecular. They can be the same kind of molecule, so don't confuse that. Sometimes we see 2 of the same molecule in the reactant side, and we think it's unimolecular because it's one kind, but bimolecular just means 2 molecules that can be the same. And so as you look at the example in your notes, both of the elementary steps we have are bimolecular elementary steps. We've got 2 molecules that are reacting. Again, elementary steps where you have 3 or more are extremely rare. It's going to, again, require those 3 particles to simultaneously collide with the correct orientation and the correct amount of energy. So it's really rare that that happens where you've got 3 or more reactants. Okay, so for example, as you take a look at your notes there, you're giving your overall reaction with the elementary steps of the mechanism sort of spelled out for you. The reactions in that mechanism, again, are elementary steps, meaning you can't break those steps down any further, and that the molecules actually interact directly in that manner without any other steps. Notice in the overall reaction, you're given, again, what you observe, but the mechanism breaks that down a little bit, and we get some what we'll learn are intermediates. Notice, for example, in the elementary step 1, we react the hydrogen with this ICl molecule, we produce the HCl, but we also produce this HI molecule, which is nowhere in the reaction. But then note in the second step that intermediate that was produced is then consumed in that second step. second elementary reaction. And because HI is made but then consumed, HI does not show up in our overall reaction. And so we, in the past, would have never recognized that this thing ever would have existed because we never would have written it as a reactant or product. But now we have to recognize that our reaction is actually taking part in all these different steps, and sometimes we produce these things that are called intermediates. And again, it's just something that is a product in an early mechanism step, but then is a reactant in a later step and is used up or consumed, and so it's not shown in the overall reaction. It's just what we call an intermediate. Okay, now it's important to note that the rate of reaction for the elementary steps is based on the stoichiometric coefficients of the reactants in that elementary step. However, and I cannot stress this enough, it's a mistake that's going to happen. You want to use stoichiometry and the balance coefficients, and the coefficients in the balanced chemical equation to write your rate laws for the overall reaction. It's so tempting to do, but remember that the rate law for the overall equation has to be determined experimentally. It's only when we have the elementary steps where we can use those stoichiometric coefficients. So keep that in mind, watch out. Rate laws for the elementary steps can be done based on the stoichiometric coefficients, but only the elementary steps, not the rate law for the overall reaction. So each step in the mechanism, just sort of treat it like its own little reaction with its own activation energy and its own little rate law. And so again, as you try to determine the rate law for an overall reaction, you have to determine that from some experimental data where you set up a series of reactions where you vary the concentrations to sort of see how the rate changes based on that change in concentration. But for the elementary steps, you can very easily just look at the coefficients in the balanced elementary reaction, or the balanced elementary step. And so as you look at, for example, step 1 in this mechanism, our rate law is the rate constant times the concentration of hydrogen to the first power, or first order, right, times the concentration of the ICl, again, to the first power, because in the elementary step, it's a coefficient of 1 and a coefficient of 1. That same thing happens here in the second step. We see that rate constant, its own rate constant, times the concentration of HI to the first, times the concentration of ICl to the first. And again, that comes from the coefficients in the balanced chemical equation. And we'll learn why that's important, because sometimes the College Board will not give you experimental data to determine the rate law for a given reaction, but it'll give you the reaction mechanism. And as we'll learn, you have to recognize how you can use those to determine what the overall rate law is going to be. Okay, so the slowest elementary step is called the rate determining step for the reaction. Sometimes you'll see it abbreviated RDS. The rate of the reaction, of the overall reaction, is dependent upon the rate determining step. So you're only as strong as your weakest link, and we're only as fast, our reaction is only as fast as the slowest step. So as you take a look at the overall reaction in your notes at this point, it has a two-step mechanism. And you'll often see, depending on the problem that you're being asked, you'll see the reaction mechanism broken down into its elementary steps, and then you'll see it sort of labeled as slow or fast, or you'll see fast equilibrium and things like that. The slow step, or the rate determining step, again, is the one that we're going to focus on, because that is the one that's going to determine the rate for the overall reaction as well. And again, we'll work through a really cool demo in class. I think will help clarify that idea. But basically, the slow rate determining step, step 1 in this example, we can determine the rate equation, or the rate law, simply by looking at the coefficients in the equation for that elementary step. So the rate law is the rate constant times the concentration of NO2 to the first, times the concentration of F2 to the first, again based on the coefficients in that elementary step. And then we're told, which means it's a second order reaction overall, 1 + 1 = 2, for this elementary step. And then we're told experimentally it is found that the reaction is second order overall, which is consistent with the slow rate determining step also being second order. So the rate determining step, note that its reaction order overall is 2, and we're told that the reaction overall is second order, and then we're told that the reaction overall is second order overall as well. And so those two things have to match up when you're doing these types of problems. The rate law for your rate determining step has to match the rate law for the overall reaction. And in addition to the fact that those two things have to be in agreement, the species or the things present in each of the rate laws has to be the same as well. As you're working with the reaction mechanisms, it's important to note that the individual steps of the mechanism must sum together to give the reaction stoichiometry of the overall reaction. Your intermediates will cancel out. So as you look at the example, it's in your notes there. Notice if we sort of sum these two equations together, because F is a product here in step 1 and a reactant here, it's an intermediate, it will cancel out, and then they sum together to give us the overall reaction with the correct stoichiometry. So notice we would have 2 NO2s on a reactant side, 1 F2 on a reactant side, and then 2 NO2Fs as well. So it's important to recognize that that is true of your reaction mechanisms. Okay, and then keep in mind that intermediates that appear in rate laws are generally replaced by the reactants that they depend on. And we'll do some example problems like this, but for example, if you take a look at your notes, in the reaction where general reaction A plus 2B forms C plus D, we have a following 3-step mechanism that is known, where Q is our intermediate. Notice that it's produced here in step 1 and then consumed in step 2. It says the rate equation for the slow step, i.e. the rate determining step, which is also the rate equation for the overall reaction, because the slow step rate law has to have the same rate law as the overall reaction. So when you write the rate law for the slow step, you are essentially still writing the rate law for the overall reaction as well. However, note that because Q is an intermediate, we're going to have to replace it, and we'll do some work with this and explain how you actually work through this, but it can be replaced by the reactant that it depends on in order to be formed. In this case, we're replacing it with A, because this rate law that was written for the elementary step, step 2, although it is correct, keep in mind that we have to the rate law for our overall reaction and the rate law for the rate determining step have to be the same, and so we can rewrite that so that it includes the reactants that we would include in the rate law for the overall equation as well.